Hello students, we're on the 8.2 ICE. And we're going to do 3, 4, 11, talk about 14, do 15. So 3 has a bunch of different problems and just wants to know converge or diverge, and I'm just going to use show you some different tests on each one. So some of them you should just recognize as P series or geometric series, like this one I think is F. You should just know that, hey, that's P is 1/2, so let's make it a 1, so that's a divergent P series. You want more than 1. Geometric would be something like n, which is written a little weird. It's 3 to the n, e to the minus n. But if you rewrite that as 3 to the n over e to the n, which is 3 over e to the n, you should know that 3 over e is greater than 1, so this is a divergent geometric series because you want it to be less than 1 in absolute value inside the n. So geometric and P series are your standard things to compare with. Well, you might use comparison test. Actually, there's so if you go to L here, there's a couple ways to do this one. This is sine squared over n, or of n over n squared. So sine is always between -1 and 1. Sine squared is always non-negative. It's between 0 and 1. So you could just say this is less than 1 over n squared by the comparison test. That's probably the easiest way to do it. I'm going to do a slight variation of that to show you what you would do in this case. Now you've got negatives. Comparison test only allows for non-negative numbers, but if you take the absolute value, that would be less than this. And so that would tell you that because that converges, that implies the original converges, because absolute convergence implies regular convergence. Also, you can't use the alternating series test because sine of n goes positive and negative, but not every other. So it's not necessarily alternating. Okay, anytime you see a factorial, you probably want to do the ratio test. So something like b is 3 to the n over n factorial. The way you're going to do this is you're going to change everything to an n plus 1 and then divide or really multiply by the reciprocal of the original. And the reason why you do this, especially for geometric or for ratio terms, is because they cancel nicely. Don't forget you're taking a limit here. Those cancel, and then all the factorials of the right amount cancel except this one. So you get 3 over n plus 1. You're still taking a limit. And that becomes 0, which is less than 1, so it converges. For ratio tests, you want less than 1. The root test is also in this book. You really don't want that unless everything is to the n. I could have used the root test on the one where I did geometric series. Maybe not everything to the n, but a lot of it to the n. Or something like n to the n you might want to do. However, if you look at E, it's the last one I'll do from this section. It's n factorial over n to the n. I don't know whether to do the ratio test or the root test. Both sound gross, but what I'm going to do is write some terms out instead. I'm going to start at 1. So you'd have 1 over 1, and then you'd have 1 times 2 over 2 times 2, plus 1 times 2 times 3 over 3 times 3 times 3. And you can see what's happening is that this is getting much smaller, much quicker on the bottom, which gives me hope that it converges. And so I wanted to try to do some kind of comparison. So if you look at these, this is, what if I did maybe 1 over n squared? It doesn't seem to work yet. But if you look at, so this, you have a 2 up top, you have a 2 up top here. This makes it less than 1. And then really the only issue is this 2, right? So why don't I just make it 2 over n squared? That's a multiple of the convergent series, so it still converges. This shrinks it even more. And I think let's do one more to verify 2 over 5 times 5. So you get 1, 2, 3, 4, 5, and then 5. So those cancel, these shrink it, and then this is 2 over n squared. So that's a comparison that works, but I would not have seen that without writing the terms out. Never be afraid to just grind these terms out. Don't try to do these in your head abstractly. Okay, so that's probably enough of number 3. Now we want to talk about number 4. I'm just going to do part A, and then you can try part B, which is similar. It says for which p-values do these converge, and it's 1 over n to the ln of n to the p. I'm going to use the integral test because the trick to this is really W substitution. So this converges if and only if this converges. The integral test, I think, is the only one that's if and only if. So these match up exactly. So I'm going to make W ln of x so that dw is 1 over x dx. And this is going to go from ln to, which really isn't that important. Ln of infinity is infinity. And now this is a p series, well, or p integral. When does that converge? That converges when p is greater than 1. So it's the same value as a regular p series. Same conditions. So that was 4a. You can try 4b. 4b is just a different W substitution that you guys can try. Okay, number 11 is a really interesting example of a specific series. This is show it diverges, and why does it not contradict the alternating series test? So 1 minus a half plus a third minus 1 over 2 squared plus 1/5 minus 1 over 2 cubed plus 1/7 minus 1 over 2 to the 4th. Okay, let's separate the positive terms. This is a divergent series similar to the harmonic series, it's just the odds, but it's still divergent. And then the stuff you're subtracting is a convergent geometric series. So really, if you look at this, this is unbounded, and you're subtracting far less than you're taking away. This is a convergent geometric, and this is divergent. So a divergent sum minus a convergent sum, that's going to be divergent still. The reason why it doesn't work, the contradict alternating series test, is if you write out the terms, you think the alternating series test has a condition that if you write out the terms without the negatives, you make it all positive. Well, it's supposed to be monotone decreasing. If you look at this, it goes 1/8 and it goes back up to a 7th. It was good at first, but now it's not good. So it can't. It has to be decreasing the whole time monotonically. There are points later where these things start flip-flopping. And so the terms do go to 0, but not monotonically. All right, for 14, I'm not going to do the problem, but I want you to take away the fact. Also, they wrote the word obvious, which annoys me. All that they're trying to say is that the ratio test and the root test work at the same time. Now, sometimes algebraically one's harder than the other, but it says whenever the ratio test determines convergence or divergence, the root test does too. That's the point. So they give the same conditions and the same results. That's the point of 14. So just take that fact away. You don't need to read the rest of the problem. Okay, and 15 has kind of a fun trick to look at. Let me grab some paper here. 15 says if a series is conditionally convergent, then the negative terms are divergent. So I'm going to do a trick here. So AN is conditionally convergent. So this is convergent, but this is not. And there's a hint in the back about making some new series, which makes this whole problem work, which it's a pretty cool trick. So they're going to define Pn to be AN plus absolute value plus regular over 2, and then Qn, you're going to take the difference. Okay, and both of these should always be positive, I believe. Okay, so notice that if Pn and Qn, we're going to try to show that these both diverge as sums. How are we going to show that? Diverge. So if they both converge, you could add them, but that would be this. which diverges. So at least one diverges. If both, so if, let's say if one diverges and one converges, well, if you took the difference, that can diverge, right? A divergent added or subtracted from a convergent would diverge. So if you take Pn minus Qn, that would have to be divergent. And I think you would get An here, which is also false. So you can't have one convergent, one divergent. So both diverge. And the point of knowing that those two things diverge is that if you look at Pn, what is this really doing? Well, when An is positive, you get the positive term again. And when An is negative, you get 0, right? So Pn is really the sum of positive terms, because negative terms go to 0, because you have the positive and the negative the same thing. Okay, so the positive terms diverge. Now Qn, when you have positive terms, they disappear, and then the negative terms, you get, how does this work? Yeah, you get the positive version, right? Qn is the positive version of the negative terms, which is really what you wanted, right? Whether you added negative or added positive, it doesn't matter, but they diverge. Okay, that's the end of the 8.2 ice sheet.